I am Dr. Piyali Chatterjee, Assistant Professor, School of Applied Science and Humanities, Haldia Institute of Technology. Now I will discuss about general features of IR absorption spectrum. As I mentioned that there are different types of vibrational modes, symmetric stretching, anti-symmetric stretching, different kinds of bending. But the general observation is that the anti-symmetric stretching vibration appears at higher frequency as compared to symmetric stretching vibration as shown here, because anti-symmetric stretching requires more energy as compared to symmetric stretching, and bending vibrations generally appear at lower frequency as compared to stretching vibration. This is very easy to understand because if we consider this cartoon, then it can be seen that it is much easier to bend an iron bar as compared to stretch it. So bending is easier, it requires less energy, and it appears at lower frequency as compared to stretching vibrations. Now, as I mentioned earlier, that there are different kinds of vibration. If we consider only the stretching vibration, then the vibrational frequency also depends on different factors. The two main factors are uh, the spring constant and the mass or reduced mass. Now, as the first we will consider mass. As the mass increases, then the vibrational frequency decreases. This is very easy to understand because heavier atoms vibrate slowly as compared to lighter atoms. So, if we consider uh, bonds between carbon with various atoms with increasing masses, as for example, if we consider CH bond, CO bond, and CCl bond, we can see that the vibrational frequency is highest for the CH bond because hydrogen is the lightest element, which is followed by oxygen and then chlorine. So the stretching frequency increases as the mass decreases. Now, the second factor is the force constant or spring constant. As the spring constant value increases, then vibrational frequency increases. The stronger the bond, the higher is the vibrational frequency. So, if we consider carbon carbon single bond, carbon carbon double bond, carbon carbon triple bond, in all these three cases, mass is the same, but carbon carbon double bond is much stronger than carbon carbon single bond, whereas carbon carbon triple bond is even stronger than carbon carbon double bond. And as a result, the vibrational frequency is highest for the carbon carbon triple bond, which is followed by carbon carbon double bond, which is then followed by carbon carbon single bond. And the same trend is followed by CO single bond, CO double bond, and also for CN single bond, CN double bond, and CN triple bond. And it also implies to CH bonds where carbon is either sp3 hybridized or sp2 hybridized or sp hybridized. That is the CH bonds for alkane, alkene, and alkyne. As we know that the CH bond of alkene is stronger than the CH bond of alkane, and even the CH bond of alkyne is even stronger than CH bond of alkene as shown here. And as a result, the CH bond of alkyne has the highest vibrational frequency. Now, in general, any vibrational spectrum or IR spectrum can be very roughly divided into four different regions as shown here with four different colors. Now, the region within 3000 to 4000 centimeter inverse, in this region, particularly absorption bands due to carbon hydrogen single bond, oxygen hydrogen single bonds, or NH single bonds, these type of bonds, bond vibrations appear particularly in this region. This is due to the fact that hydrogen is the lightest element. So all these CH, OH, NH bonds, they have higher frequency or the highest frequencies, vibrational frequencies, and they absorb in this region. Now, the absorption bands appearing in the range of 2000 to 3000 centimeter inverse are generally due to triple bonds, carbon carbon triple bonds or carbon nitrogen triple bonds. And here, the bond strength factor is actually effective, because these triple bonds are very strong and they do not include hydrogen also. That is why they appear at the higher frequency range. Now, the absorption bands appearing in the 1500 to 2000 centimeter inverse are due to single bond, or carbon carbon double bond, or carbon oxygen double bonds. And there it is also due to the fact that double bonds are less stronger as compared to triple bonds. Therefore, these double bond vibrations appear at slightly lower frequencies as compared to the triple bond vibrations. Now, the region below 1500 centimeter inverse are particularly due to single bonds that do not involve hydrogen atoms. That is the CC single bond, CO single bond, and CCl single bonds. And again, these single bonds are much weaker than double bonds, and they also do not include hydrogen atoms, and that is why they appear in the lowest frequency range. So, these are the four different regions uh, appear for the IR spectrum, and from the position of the absorption bands we can basically identify which type of bonds or which functional groups are present in the molecule. Now, there is a specific region in this IR spectrum which is below 1500 centimeter inverse, which is called the fingerprint region. Now, as shown in this spectrum, this particular region is very much congested, and this is the general feature for any IR absorption spectrum. There are too many peaks, and it is not possible to assign each individual peaks in this region to a particular bond vibration. Rather, the arrangement of peaks in this region is unique for each molecule. Therefore, we can basically compare the arrangement of peaks, which is basically just like one person's fingerprint, and that is why it is called the fingerprint region. So, if we compare the arrangement of peaks in this region for different molecules, then we can actually identify the molecule for which this absorption spectrum appears. So, not only we can identify the different kinds of groups and functional groups are present in the molecule from IR spectrum, we can also identify by comparing IR spectrum in the uh, fingerprint region. Now, I will discuss about how any absorption band look like. Uh, that is, what is the particular height and width of an IR absorption band. As shown here, IR absorption band could be much stronger, or with medium height, or could be much weaker. The intensity could vary. Now, the larger the intensity or strength of the IR absorption band, higher intensity of IR radiation has been absorbed by the chemical bond. These bonds are generally designated by strong, medium, and weak, and these are represented by the letters S, M, and W respectively. So, higher the strength of the IR absorption band, higher the intensity of the IR light has been absorbed. And this is basically due to the fact that with the change in the dipole moment with vibration is much larger in case of a strong or intense IR absorption band. The higher the change in dipole moment with vibration, the stronger the IR absorption band is. And that is why more polar bonds uh, give rise to stronger absorption bands as compared to less polar bonds. Now, the width of the IR absorption band. This is the IR absorption spectrum of water. We can see that the weight stretching vibration as appearing here is very much broad, and this is due to the presence of hydrogen bonding within water, as shown here. Now, for water and for other alcohols, these molecules are intermolecularly hydrogen bonded, and as shown here, as a result, this OH bond distance varies. As for example, this OH bond distance is changing, it is increasing and it is decreasing. And as a result, the OH vibrational frequency also changes, and the IR radiation that is absorbed by this wave vibration, that also changes, and that is why this wave stretching vibration appears to be very, very broad. Now if we consider another alcohol, which is butylated hydroxytoluene, in this compound we can see that on both side of this hydroxyl group there are two bulky tertiary butyl groups, which prevent these molecules to come closer and to form hydrogen bonds. Therefore, these molecules do not form hydrogen bonds, and the weight stretching vibration, as can be shown here, is quite sharp here. So, the final takeaway is which information we can have from IR spectroscopy. From the position of the IR absorption bands, we can identify specific bonds or functional groups present in the molecule. And when we compare the fingerprint region, the absorption bands or unique absorption features appearing in the fingerprint region, that is below 1500 centimeter inverse, we can unambiguously identify the molecule present in the sample. We can also have information about the characteristics of the bond, because the force constant, it represents the strength of the bond. Intensity of the IR absorption band represents polarity of the bond. And also we can distinguish between different isomers, because isomers have different masses, and that is why they will have different vibrational frequency and they will absorb different IR frequencies. We can also identify whether there is hydrogen bonding or not from the width of the IR absorption band. Apart from all these informations, IR spectroscopy can also be used for quantitative analysis. Now, this is all. Thank you all.